Okay, guys, as we go through these answers, please feel free to unmute yourself if you have any questions. Also, please keep in mind that during the lesson today, I'm actually going to have some polling to make sure you're kind of paying attention. So hopefully you'll be doing that. The questions are pretty straightforward, and then there will be an exit slip at the end. So for question one, we're going to kind of go back to Calc 1. Hopefully, if you check this, if you just did a direct substitution, I would call it DS, you will get, I think you end up getting 0 over 0, which is not good. That's what we call an indeterminate form. 0 over 0 is an indeterminate form. We're going to use those words a lot today. I'm actually going to try to focus on some of the different indeterminate forms than that. So what we could have done back then is you would have factored. The numerator had a 3x in it, so you could factor out an x minus 7 in the numerator. And of course, the bottom is a difference of squares. Difference of squares, so we can do our sum and difference pattern. And then the x minus 7s cancel. And now we can do our direct substitution with the 7. So we're going to get 21 over 14, which is equal to 3/2. So that's the answer to number 1 without a calculator. Number 2, I claim that you should just know that that's 1. This is one of the limits that you were asked to memorize way back in Calc AB when you did chapter 1. There was actually another one that involved cosine. Let's not worry about that. We actually use something called the squeeze theorem. I can spell squeeze. The squeeze theorem to prove that in chapter 1. And once you get to number 3 here, we run into an issue because if we just do a direct substitution, you are going to get e to the 0 minus cosine of 0 over 5 times 0. Well, that's going to be 1 minus 1 over 0, which is, again, 0 over 0. So this is when we start talking about our good friend L'Hopital. And that's what we're going to talk about today. And in order to find the answer to this, we're going to basically differentiate the numerator and the denominator to find the answer. And I'm just going to go ahead and tell you the answer to this last problem is 1/5. You probably were able to figure that out on your own. But I'm going to save the explanation of L'Hopital here for in just a second. I felt like there was something else I wanted to say there, but I'm drawing a blank. So does anyone have any questions on the warm-up? Oh, I know what I was going to say. The reason that we don't cover L'Hopital until later in the semester is, like, so for example, here, I asked you, if you had me last year, to memorize this in chapter 1. In order to do L'Hopital, what do you have to use? Differentiation. Well, when you were doing chapter 1 back when you were in Calc AB, you didn't know differentiation yet. So it's actually impossible for you really to be able to use L'Hopital if you don't know what differentiation is in the first place. Okay, so let's go ahead and get started here. A couple of important announcements I actually want to make before we start doing examples. Number 1, next week you will have a test, and that test will cover chapter 6 and chapter 7. Now, I'm going to, again, you may really want this PowerPoint just to have this information, but the test will cover section 6.2, that's volumes. We already had a quiz on that. And section 6.4, which is on arc length and surface of revolution. We've had a quiz on all of this stuff. So this is basically a continuation of the quiz. Then in chapter 7, it's going to be section 7.2, which is, I think it is not use substitution. And now I'm drawing a blank again. Integration by parts, thank you. Integration by parts. Section 7.3 is on trig integration, and section 7.4 is on trig substitution. Partial fractions will not be on this test, and none of the stuff that we do today will be on the test. So the test that you take next Tuesday during this class period is those 5 sections. So you've already spent plenty of time looking at these, and you should have a pretty good foundation of these. And remember, this is all virtual. So if you need to have like a little cheat sheet or two to help you remember some of those key formulas and identities, you can. Remember to follow the correct testing protocol, which is to log in with your school Chromebook, with your school account, with the camera on and the microphone muted. And I would also encourage you to make sure that you have your Chromebook in good shape. For example, today, mine, when I booted it up, said, hey, you haven't restarted your Chromebook in a while. And so I did that. I want to make sure your Chromebook's working well so that you don't run into any issues during the test. The other thing that I want to mention, the second important announcement, is I made an announcement in the Canvas page, and I've already had one of you kind of ask me about that. You need to read that announcement. It pertains to missing work and makeup work. If you have no missing work or makeup work, you don't need to worry about it. But if you do, you want to read that announcement, and I'm just going to mention this important date so that I can say later on, I told you so. Friday, December 11th at 9 p.m. That is an important date and time. All right, without further ado, let's go ahead and get into L'Hopital. L'Hopital's rule, and L'Hopital was the name of a mathematician, says suppose that f and g are differentiable functions and g prime isn't equal to 0. So if the limit of the f function is 0 and the limit of the g function is 0, then the limit of their quotient is equivalent to the limits of their derivatives. Or if the limit of f goes to plus or minus infinity and the limit of g goes to plus or minus infinity, then again, the limit of, or the quotient of those functions is equal to the derivative of those limits. So the condition for L'Hopital to work is you basically need to end up with 0 divided by 0 or infinity divided by infinity. These are the two indeterminate forms, the basic indeterminate forms, that I would have worked with you last year in terms of Calc AB. So if you have these indeterminate forms, then you may proceed and go ahead and use L'Hopital's rule. I caution you on using L'Hopital's rule when you don't need to, because you can actually end up with an incorrect result. Note, L'Hopital's rule says that the limits of a quotient is equal to the limits of the quotient of their derivatives. This is provided that the given conditions are satisfied, so this is very important. Note number 2, L'Hopital's rule is also valid for one-sided limits. So if you're having to do a limit to infinity or negative infinity, and you want to go a plus, a minus, it is also valid. And you might think, okay, why would I want to do that? Well, you're going to see when we get to section 7-8, we're going to talk about improper integration. And we're going to have to do integrals where there are vertical asymptotes and such. And so we're going to have to use this rule in some of those situations. So let's go ahead and look at a simple example here. And in this example, example number 1, the first thing that I always encourage my students to do whenever they have a limit like this is just to go ahead and try direct substitution. So you're going to have the ln of 1 over 1 minus 1. Well, that's going to be 0 over a 0. And that is an indeterminate form. This is an indeterminate form. So we can see that this numerator is 0. This denominator is equal to 0. So when you get 0 over 0, the answer could literally be anything. It could be 0. It could be a billion. It could be D&E. It could be anything. So now what we're going to do is we're going to go ahead and go to the hospital. We're going to use L'Hopital's rule. And L'Hopital's rule says this: if we have one of these indeterminate forms, we can go ahead and say that the limit as x goes to 1 of the ln of x over x minus 1 is equivalent to the limit as x goes to 1 of the derivative of ln of x, which is 1 over x, divided by the derivative of x minus 1, which is just 1, which is simply the limit as x goes to 1 of 1 over x. So clearly now we can just do a direct substitution here and we get the final answer of 1. So this is an easy example, probably the most basic example I can think of for using L'Hopital's rule. Okay? So the answer for the limit for example number 1 is 1. Please feel free to unmute yourself if you have any questions throughout the presentation. Okay, so this first example is kind of what last year I would have emphasized, where it's 0 over 0 or infinity over infinity. The rest of this presentation, I'm actually going to kind of move away from those indeterminate forms. So let's talk about indeterminate products. So instead of 0 over 0 or infinity over 0, what if you end up with something like, and I'll just go ahead and highlight what this is going to be an example of, is the indeterminate form of 0 times infinity. Now, intuitively, you might want to say that 0 times infinity is 0, but you would be incorrect. That is not necessarily the case. So it turns out if the limit of f of x is 0 and the limit of g of x is infinity or negative infinity, this is also an indeterminate form. Oh, and I should mention, I posted a very interesting YouTube video on the extra video part of or extra videos for this section. And I can't remember the words I used precisely, but something like must watch. It's kind of long, but it's really, really good. Okay, so let's go ahead and here's how we're going to deal with these indeterminate products. We're going to change the product into a quotient. And the way that we do that is we just do the reciprocal of g, or if we need to, we could do the reciprocal of f. That's going to turn us back into the quotient. And once we have a quotient, then we can get into L'Hopital's rule. So let's go ahead and look at example number 2 here. Example number 2 says the limit as x goes to 0 plus of x ln of x. So let's do a direct substitution here. So we're basically going to get 0 times, and now what is 0 plus? Well, if you think about the ln function, which I'll go ahead and sketch the graph of right here, this is the ln function. Where does ln go as we get closer and closer from 0 on the right-hand side? Well, it's going to actually be negative infinity. So that's going to give us an indeterminate product. An indeterminate product. And since this is an indeterminate product, we have an issue here. So what we're going to do is we're going to rewrite this. So we're going to take this limit as x goes to 0 plus x ln of x, and I'm going to write it in kind of a clever way. I'm going to make this the limit as x goes to 0 plus, and I'm going to leave the ln of x on the numerator, and now I'm going to change this x to 1 over x. Now I'm going to show you that when I do the limit, and let me do this in red here, if I do the limit as x goes to 0 plus of the ln of x, what's that going to go to? Well, again, if we're looking at this function here, this is going to go to negative infinity. If I do the limit as x goes to 0 plus of the denominator, which is 1 over x, what's that going to go to? Well, if we were to graph that function, which I'll go ahead and do that as well over here, the graph of 1 over x looks like this. If I'm going to 0 plus, where's that going? Well, that's going to positive infinity. So in other words, I've got negative infinity over infinity. So this right here is an indeterminate form. So now we're going to have to go to L'Hopital. So let's go ahead and use L'Hopital's. L'Hopital, if I can spell it correctly, is going to be the following. The limit as x goes to 0 plus of the ln of x over 1 over x is going to be equal to the limit as x goes to 0 plus. The derivative of the numerator is simply 1 over x again. We've seen that now twice. When we do the derivative of the denominator, we're going to get negative 1 over x squared. Now we can go ahead and clean that up a little bit. In fact, let me go ahead and show a little bit of work. Remember, when you divide a fraction, you simply multiply by its reciprocal. So that's just going to be negative x squared over 1. And when I multiply those two guys together, clearly you're going to see that the x's are going to cancel, and you're going to be left with negative x. So this limit right here is going to become the limit as x goes to 0 plus of negative x. And of course, if we go to 0 here, the answer is just a 0. So the answer here is 0. So now here's the interesting thing. Let's go back to the original question here. The original question was, what is the limit of the product? Remember, this is a product, x times ln of x. So I've got this function x, and I've got this function L of x, and I claim that in this case, x beats the ln of x. X beats the ln of x. Okay, I'm going to launch a poll question here, and I'd like you to answer it. Oops, someone hit me up here. Sorry about that. Let me see what you said. Oh, give me, I'll get to that later. Okay. By the way, this is example 2.
Oops.
You put in the wrong answer, James, by accident?
Yeah, I thought that was example 1.
Yeah, sorry. That's okay.
Mr. Allen?
Yes.
I think my internet went really slow when you were explaining why we turned x into 1 over x.
Oh, here? To here?
Yeah.
Yeah. So what we're trying to do here, James, is we're actually trying to convert this product into a quotient. And so what I'm doing here is, think about it this way. If I multiply this by x over 1, right? You with me?
Yeah.
The reciprocal of 1 over x is x over 1. So if I multiply this, now the denominator is now 1, correct? The numerator is now x over ln of x. So what I'm telling you is this, is that x times the ln of x is equivalent to the ln of x divided by 1 over x.
Okay, thank you.
All right, so so that gives us example 2. So as I said in example number 2, we got a final answer here of 0. And again, I claim that x beats the ln of x. Okay, so another note I'd like to make about this example before I move on is that in solving example 2, another way we could have done this is instead of taking 1 over x in the denominator, we could have done 1 over the ln of x. This gives us an indeterminate form of 0 divided by 0. But if we apply L'Hopital's rule here, we get a more complicated equation. In other words, what I'm saying here is if you're not careful, if you do it this way, you actually make things worse. So if you've got the option, you want to try to make it to where when you find the derivative, it's actually an easier derivative. Okay, so we just did products. Now I want to talk about indeterminate forms involving differences. So if the limit of f of x is infinity and the limit of g of x is also infinity, then the limit of their differences, infinity minus infinity, is also an indeterminate form. So let me highlight that here. Oops, that's the eraser. Let's try that again. This is an indeterminate form of infinity minus infinity. Now you would probably intuitively think that infinity minus infinity would be 0. You would be mistaken, though. That is not necessarily the case. It could be 0, but it actually could be infinitely other things as well. So with will the answer be if f wins? So in other words, if f wins, it dominates. Will it be negative infinity? Or if g wins, it depends. Believe it or not, there's actually different sizes of infinity. So that's what you've got to kind of figure out here. And we're going to play kind of the same game we played in the last one. Let's look at an example of that. So this one's going to be a little tricky, and so I apologize for that. I'm going to end this poll. Okay, good. All right, so we're going to do a trigonometric one here. So it says compute the limit as x goes to pi over 2 negative. So this is, again, a one-sided limit. We're doing secant x and tangent x. And you know what? Maybe just to review, and maybe I shouldn't spend too much time on this, but if you think about the tangent curve looks like this. And then if we did the secant curve, let's do the secant curve maybe right here. Here's the secant curve. The secant curve looks something like this. And by the way, this right here, this is a vertical asymptote, and this is a vertical asymptote that turns out to be at pi over 2. And this is also at pi over 2. So if I did a direct substitution into this particular problem, you are basically going to say, okay, what is secant going to go to as we go to pi over 2 from the left? Well, it's going to infinity. What about tangent as you come in from the left? Well, that's going to infinity as well. So you can see here that we have this indeterminate form that we just mentioned that is infinity minus infinity. So this is I'll put a question mark here. This is an indeterminate form. So now we're going to have to do a little bit of work to get things to work out better for us. So what we can do is this. We can rewrite, I'm going to do a little trigonometry again. We've done a lot of that, it seems like, lately. Pi over 2 negative, oops, not squared. Pi over 2 negative of secant x minus tangent x could be thought of as the limit as x goes to pi over 2 negative of, I can change secant x as 1 over the cosine of x minus, and then of course I could change tangent to sine over x cosine over x. Now that's nice because, and I'm not going to write the bottom of the limit here. Now I have a common denominator and I can say that this is 1 minus sine x over cosine x. Now it turns out that if we went ahead, I'll go ahead and add it just in case. If we went ahead right now and did direct substitution, this particular limit right here is going to end up giving us 0 over 0, which again is an indeterminate form. So this is an indeterminate form because this is going to go to 0. This denominator is going to go to 0. So we're going to have to go to the hospital again. So we're going to do L'Hopital. So this limit, and I'm going to go ahead and rewrite it. The limit as x goes to pi over 2 negative of 1 minus sine x over cosine x. I'm going to do the derivative of the numerator and the denominator. The derivative of 1 is 0. The derivative of negative sine is going to be, if I'm not mistaken, I think that's going to be negative cosine. And then the derivative of cosine is going to be negative sine. Of course, the negatives are going to cancel. And we'll get the limit as x goes to pi over 2 negative of cosine x over sine x. Oh, and by the way, what is cosine x over sine x?
Cotangent.
Cotangent, thank you very much. So this is cotangent. So that's cotangent. And then the cotangent of pi over 2 turns out to be 0. So this answer is 0. That's a 0. The cotangent of pi over 2 is 0. If you wanted to, you could have just done the cosine of pi over 2 for cosine, and then the sine of pi over 2, and you will get the same answer. You get 0 over 1. 0 over 1, which is 0. So this was to show an example of infinity minus infinity. Okay? So we've looked at the product of that yields indeterminate form. We've now seen a difference that yielded an indeterminate form. Oh, I guess I have another poll here. These are fun. Okay. This poll's a little bit more challenging. Please put what you think is the best answer. And don't stress out if you're not sure. It's completely okay to say, I'm not sure. Okay, go ahead and finish up answering the poll. Again, please just put what your gut instinct is on there. This isn't a test or anything. I'm not actually grading this. Got about 15 minutes left. That's good. Okay, I'm going to go ahead and continue on here with our next part. The last thing I want to talk about is indeterminate powers. So we started the lesson with talking about 0 divided by 0, infinity divided by infinity, which is basically what L'Hopital is based on. We looked at indeterminate products. We looked at indeterminate differences. And I want to mention indeterminate powers. So there are 3 different types here that we could have, and I think I'll just highlight those right now. All 3 of these are indeterminate forms. It turns out that 0 to the 0 power is an indeterminate form. That is one that most students would probably think that seems like that should be 0, Mr. Allen. If you think that, I would like to ask you this question. What's 2 to the 0? What's 3 to the 0? What's 742 to the 0? This second one, infinity to the 0. Infinity to the 0, you'd think maybe that should be 1. Well, that is actually not necessarily true. And 1 to the infinity, you would think that this would be 1, wouldn't you? Shouldn't that be 1? It turns out that all 3 of these are indeterminate forms, and it depends on the functions, whether or not they exist or don't exist or what they equal. So if you want to think about it, the base is 0 and the exponent is 0, 0 to the 0 is an indeterminate form. If the base is infinity and the exponent is 0, this is again an indeterminate form. Each of these 3 cases can be treated by either taking the natural logarithm. So this is going to be the key to these problems. And I'm going to just let you know right now, I think these are the hardest ones. And I'll do an example, hopefully, to give you kind of a flavor or the taste of what's going on. In other words, what we're going to do is we're going to take y equals f of x to g of x, and we're going to use this rule. In fact, let me just show you the rule. The natural log of x to the second, I hope you guys all know that's equivalent to the 2 times the natural log of x. You probably recall that rule. Obviously, this is a concrete example of it, but that's what we're going to use here. Okay, and then obviously once we get to something like this, then we're back to that product, if you will, that product example we did earlier. So let's go ahead and look at, this is my last example here. We have about 12 minutes, so that's great. And I'm just going to forewarn you, this one's kind of beefy. It's kind of involved. So as you can see, I've got 4 sine 4x inside the parentheses in the base. And then I have this cotangent out here as the exponent. So what I would like to do first is simply say, I'm going to say note, and I'm going to say that the limit as x goes to 0 plus of 1 plus sine of 4x. Well, let's see here. If I plug 0 into that, that tends to go to what? Well, that's going to go to 1, right? If you plug 0 in here, sine of 4 times 0 is sine of 0, which is 0. So that's 1. So that tells us that this base here is 1. So that's the base. Okay, so I'll say note 1. Note 2, if I do the limit as x goes to 0 plus of cotangent x, And just a second ago, I just talked about cotangent. But it turns out that the cotangent, as x goes to 0 plus, is infinity. So this is going to be the exponent. In other words, this tends to go to 1 to infinity. And as you can see, that was one of the types I said that is an indeterminate form. And since it's an indeterminate form, we're going to have to go to the hospital. Okay? Now, guys, I'm actually going to, maybe I'll try to write small. And I apologize, guys. If I'm writing too small, let me know. I'll erase this. But I wanted to write this on here. This is important for you to do because this tells us we have an indeterminate form. And that's the first thing you always want to do, in my opinion, when it comes to dealing with L'Hopital. Okay, so now I'm going to go ahead and draw a line here, and I'm going to start working on this guy. And the way I'm going to start is this, is I'm just going to say y equals 1 plus sine 4x to the cotangent of x. Oops. That looks pretty bad. Let me fix that. Okay, and all I've done here is I've taken the function that I'm looking at and I've just set it equal to y. So here comes the trick, if you will. What I'm going to do right now is I'm going to do the ln of both sides. So I'm going to have the ln of y equals the ln, and now I'm going to do all of this stuff, which is 1 plus sine 4x cotangent x. So I am lning both sides per that last slide that I just mentioned. Now, what this allows me to do is on the right-hand side, I can now pull this cotangent x to the front of this. So now what I've done is I've moved away from having an exponent to deal with to a product. Now what I can do is I can go ahead and start dealing with the limit again. In fact, let's just go ahead and do this. Let's do the limit as x goes to 0 plus. And I'm going to play that trick that we played earlier when we talked about products. And when we talked about products, we talked about doing the reciprocal of cotangent x. Do you guys recall what the reciprocal of cotangent x is? It's tangent x. So now I can go ahead and do the tangent of x. So I'm going to leave the numerator as 1 plus sine 4x. And now the denominator, I can think of that as 1 over the tangent of x. Oops, that's not right. If I bring this down to this right now, this is going to be what? This is cotangent of x. The reciprocal of that is going to be tangent of x, correct? So when I bring that down to the denominator, it's going to just be tangent of x. Okay, I didn't explain that very well. So the reciprocal of cotangent of x is tangent x. And since I'm bringing it to the denominator, that's what we want to write. We're not going to write 1 over tangent x. It's just going to be tangent x. If I bring this tangent x up to the numerator, it would become cotangent x. Someone just hit me on the chat here. Sorry. I thought. Okay, no, I guess not. Sorry. Okay, so at this point here, if I go ahead and did a direct substitution for the denominator and the numerator, like so, when I plug 0 into the numerator, this is going to be 0 plus 1. And what is the ln of 1? It's 0. So this is going to go to 0. If I plug 0 into the denominator, this is also going to go to 0. And so guess what we have? We now have the indeterminate form of 0 over 0. The reason we want to do this now is now we can use L'Hopital. L'Hopital's rule is specific to quotients. So whenever you're going to use L'Hopital's rule, you need to make sure you have it written as a quotient. So now I'm going to go ahead and draw a vertical bar here, and I'm going to kind of continue up here on this side. So now I'm going to do the derivative of the numerator and the denominator of this expression right here. The numerator and the denominator. Okay, so this is going to be equal to the limit as x goes to 0 plus. So the derivative of the numerator, since this is ln, that's going to be 4 cosine 4x divided by 1 plus sine 4x, which makes sense, right? When you do the derivative of ln, you take what's inside the parentheses and bring it to the denominator, and then you just have to do the derivative of the inside. The derivative of sine is cosine, but don't forget you have to do the chain rule. Now we still have to do the denominator, or the derivative of the denominator, and the derivative of the denominator is secant squared. All right, so now we just got to plug things in. We're going to now do direct substitution. In fact, let me write that in red. I'm going to just do direct substitution now. And so here we go. We are going to have 4 cosine 4, and instead of x, I'm going to put a 0. And then we're going to have 1 plus sine 4, and then again a 0. And then in the denominator, we're going to have secant squared of 0. This is going to go to 4. This is going to go to 1. And this is going to go to 1. So our answer here is 4. But unfortunately, that's not the correct answer. So this is I told you this was kind of an interesting example. Don't forget that way back over here, we said that the ln of y is equal to all that jazz on the right, correct? Therefore, we would say that the ln of y is equal to 4. And we got to figure out what y is. Well, how will we get rid of the ln? We would e both sides. So the limit is e to the 4 power, which, in case you're interested in what that decimal approximation is, it's going to be 54.59815 if you're interested. Okay, good. So what I've tried to do here is I've tried to do a variety of limits. I've done, and all of them have involved L'Hopital. Some of them have been pretty straightforward. If you think about the very first one we did, you probably could have done that one in your head. And then we see one like this that's really involved. This is a very challenging one. We play this game of just using the natural log function. That's all I have in terms of examples. I'm going to go ahead and we've got 2 minutes left in class. I'm going to go ahead and send you the link to the Google form. And you can complete that. And once you're done doing that, you are free to go. If you want to stick around and ask me some questions, I will be glad to answer those questions, or at least try to answer those questions. And hopefully there is a Google link now in the chat for you, or a Google form for you to answer in the chat. Hey, James, can you mute yourself, please? Ooh, and I need to turn off the camera here.